Hello, today we are going to talk about probing. So I'm pretty excited about this topic because uh, I think this is a very useful tool for understanding and interpreting the intrinsics of the model. And probing allows us to explain what happens inside the models in terms of which layers and which types of information is contained in different components of the network. And there are potentially wide applications of probing. So today, let's first talk about what is probe and how to do the probing. And then we can look at some applications of probing. So initially, probing was introduced as a classification task. So this task is an auxiliary classification task based on the trained models. So they already have a lot of pre-trained models, and they want to understand what information is contained in, or what knowledge is contained in different parts of this model. So they attached some additional classifiers. So they use the pre-trained models to generate representations and use those representations to train the auxiliary classifiers. So when training the small classifiers, the original deep models are kept unchanged. And in this 2016 paper, they want to query whether this large model contains some specific semantic information. So they input a specially crafted sentence encoded by, for example, %, and they want to let the models to predict a label. And if this sentence representation is good, then this should allow high classification performance. Otherwise not. The data, they collected a lot of data. And let's look at several examples. So these two classification tasks are referring to whether this sentence contains the word professor as an agent of the word recommend, or whether this professor in the sentence involved this act of recommending. These two questions are slightly different. Following are some examples. Like this professor that did not like the school recommended the researcher. So the professor here is both an agent of the action recommend and also involve the act of recommending. But if the professor didn't recommend the researcher, then although the professor is still an agent, he does not involve in the act of recommending. So Q2 should be false in the second sentence. However, in the third sentence, that's good that like the professor recommended the researcher. So the agent of recommendation is the school, it's not the professor. So the professor is not involved in either as an agent of the recommend or the act of recommend. So both questions should return false answers. So the models are supposed to take in the sentence, produce an embedding of the sentence, and then pass into the diagnostic classifier. And the diagnostic classifier takes in this sentence representations and tries to predict the true or false labels, as well as other tasks. So in these three tasks, they examined the different embeddings. Glowback, a standard static embedding, a parallelogram, is similar to the Glowback, and also skip dot. This is contextualized embedding using some LSTM. And the has-school and has-human tasks are easier for the models. These are basically detecting whether this sentence contains whether it's school or human. But school as agent task requires the model to encode some of the semantics. So you can't just tell apart whether this, so you can't simply get high performance by detecting whether this sentence contains some certain words. Because as we have seen in the previous sentence examples, even if the sentences can contain very similar words, they could mean very different things. Like the school can be the agent, or the school can be present in the sentence, but the school is not the agent. So from this task, skip dot does much better than the glowback and paragram. So this was expected because only the skip dot is the only one of the three that contains the that considers the context of the previous and following words of the corresponding words. And later, other people have used probes as diagnostic classifiers. So they, in this paper, they probe additional tasks and they want to know whether the translation or language modeling produces some embeddings or the representations that contain more syntax. So in order to figure out the syntactic knowledge from the embeddings, they probe the part of speech and CCG super tagging on the pen tree banks and CCG banks correspondingly. And they also add the word identity task, which is a pretty interesting task. They take the embedding of the word I and I plus minus 1, plus minus 3, plus minus 5. This is the word I and its several neighbors, and try to predict the word I among the around 1K vocabulary. And the task setting is to probe the hidden states of the long-short-term memory. And the LSTMs come from either language modeling or translation. So the previous two papers are using probing as diagnostic classifiers. They try to detect whether the representations are capable of doing something. And this paper uses another formulation of this target. The Hewitt and Manning in 2019 attempts to find the syntax instead of diagnose the performance. So finding syntax is slightly different from the diagnosing whether these representations contain syntax. And finding syntax tries to recover the syntactic distances between the words in the sentences. So the syntactic distance is has multiple possible definitions, and they're using the distances on the syntax trees of the dependency parts of those sentences. And they want to let the probing classifiers take in the contextualized representations of these two words and try to let it predict the syntactic distances. And they want to minimize the distance of the predicted and the true syntactic distances. And they found out that the probe as a linear transformation can actually do it pretty well, especially in the corresponding, especially in the corresponding layers. So they measured how well the probes are able to recover the syntactic distances using UUAS, higher is better, and Spearman correlation, also higher is better. So in this figure, they found out that there are some layers that are doing much better than the other layers. For example, in Elmo, lower layers are better. And the 12-layer BERT around layer 6 to layer 8 are good. And the 24 layers BERT has the best syntactic distances encoded in around layer 15 to layer 19. So apparently, there are some intrinsic mechanisms in the very deep networks. They first assemble those information into the into some more abstract, into some forms that are easier for the models to process, and later, in more than the half of the total layers, their assembled forms are easier to recover the syntactic distances. And as they go towards the higher layers, the representations seem to be assembled into a form that are again harder for finding syntax. So this paper examines this effect further. So they found out that different layers of the contextualized representations actually resembles the classical NLP pipelines. So initially they assembled from some part of speech constituency dependency, and in the later layers they assembled the more semantic features like the semantic roles, co-reference, and relations. How did they find out that? They computed some summary statistics. For example, the expected layers that the model is starting to classify correctly a feature, and the center of gravity, which is the expected center of gravity for the neurons that can classify correctly this label. So the finding echoes the classical NLP pipeline. So lower level are handling syntax and then also extracting some features that are easier to process for the higher layers. And the higher layers are processing more of the semantics and preparing the representations for an easy process of the final task prediction. So up to now, everything about interpreting the probing results are just almost linear. So whenever the probing has good results, it means that the representations contain rich information. But this paper in 2019 challenges this idea. So what if the probe itself learns the task? Because the probe itself is also a neural network. Although people are using some simple neural networks like logistic regression or even or some like one hidden layer, two hidden layers, very simple networks. These networks might have limited capacities, but they are still neural networks, and the neural networks might have the potentials to learn the task. So the high diagnostic classification accuracy might be confounded by the abilities of the probe. So in order to go around this problem, they proposed to use selectivity to design the probes. So according to the arguments, a good probe should achieve high probing accuracy and at the same time, low accuracy on the control task. The control task is something new that they propose to also consider it in the probing experiment. So the control task is basically the probe still taking the same representations, but they predict random labels. And they define selectivity as the improvement of accuracy from a control task. So if a probe has high improvement from a control task, this means that the probe learns a lot from the from the useful information in the representations instead of the just random information. And as they found that as we are using more complicated multiple layer perceptrons, the neural network probes become so powerful that even if they are classifying the control task, aka random features, they can do very well, more than 90% accuracy. So using more complicated probes do not make too much sense anymore, because they are, although their accuracies are high, they basically don't tell us too much information about whether this representation is good. So instead, they propose to use as simple classifiers as possible if we are measuring the improvement of the accuracy. But everything in this paper was empirical and based on intuition, and we are going to give a formal explanation using information theory later. So the intuition for forming this whole problem in terms of information theory sort of comes from this paper in 2017. So they mentioned a viewpoint regarding the diagnostic classifiers. As we go up along the deep neural networks from the input to the output, the total information is lost because of the information processing inequality. We can't add information into a pipeline. We can only add noise and the total information is lost. But the useful information is largely preserved. So as we go up along the deep neural networks, the proportion of the useful information is actually increasing. So it might be easier for the for the diagnostic classifiers to extract the information. And the probes as a diagnostic classifiers essentially ask this problem: is there information about the feature X in this part of the model? So this intuition sort of paves the way towards understanding the intermediate layers using linear classifier probes. And by the way, they are using linear classifier probes instead of more complicated DNNs. But their ideas can generalize to different types of probes. In 2020, this paper in ETH presented this framework for diagnostic probing. The overall goal is to approximate the mutual information between the representation and the target. This actually makes a lot of sense, because if there are a lot of useful information in this representation, then this representation should have a lot of mutual information, should have a high mutual information with the target label. So this definition sort of quantifies the useful information that were mentioned in Alan Benjo 2017 paper. And what are the diagnostic classifiers approximating? So they are measuring the cross entropy loss, and they are approximating the prior the true unknown prior, let's say P, using a parameterized neural network, or the linear classifier Q, and we use data to describe the parameters. So the cross entropy loss, let's write in H, P, and Q, is the expectation of, it's basically the negative log likelihood. And note that the mutual information term that they propose to approximate can be formulated into a constant term minus conditional entropy. So the conditional entropy equals the cross entropy that we can measure minus an unknown intractable KL divergence. And this KL divergence is non-zero, and it's non-negative. But if we are measuring the cross entropy instead of the true unknown entropy, then we're basically assuming ignoring the KL terms. So the KL terms brought in some errors. So instead, in order to minimize the KL terms, they should make this KL term as small as possible. And ideally, if the probe models reaches higher performance, then this KL term should be small. And in order to minimize this KL divergence, basically they should use the best probing model as possible. So according to Pimentel paper, people should choose the more complicated models in order to minimize the KL terms. Later, we'll give an argument to as a rebuttal to this reasoning. But let's first look at whether we should look at the KL terms in the first place. So let's rearrange the terms a bit. So let's move the mutual information terms, mutual information between the T and R to the right-hand side and the cross entropy to the left-hand side. And yeah, there is a typo. It should be mutual information between T and R is not the T given R. There are two typos here. I will correct the slides later. And the so the left-hand side is the cross entropy that basically measures the probing task performances. So if we see that the probing task performance is high, then the left-hand side cross entropy is small. Then usually people just say this is because there is a large mutual information between the target and the representation. But on the other hand, a small left-hand side could be also caused by a small KL divergence between the posterior and the prior. So these two possibilities exactly correspond to the dichotomy by here and now. So if you see a good probing performance, this could be result from either the representation is rich or the probe learns the task. And additionally, should we select the probes with the high accuracy, or just should we select the probes with the high selectivity? We showed that selecting the models, as long as you are doing the control task, whether you are selecting from the random control task or control features, are basically equivalent as long as you are randomizing in the correct manner. And because if you're randomizing either R or T completely, you cut the causal chain from R to T, and both the methods of Hui and Liang and Pimento paper can be represented in this equation. So we are measuring the left-hand side and trying to use that to approximate the right-hand side. And the right-hand side is the mutual information term that we want to measure minus delta, that's the error term. We hope that the error terms are equal to 0, but they are they contains two unknown KL terms, and we definitely hope that these two KL terms can cancel out with each other, but unfortunately, it's not possible to directly estimate that. So up to now, there's a consensus that we should take a control task in addition to the probing task, and we should look at the performance increase from the control task to the probing task. Although this incrementation still has error, but approximating using this incrementation instead of only the performance of one probing task is better. So this paper introduces an argument that gets around the problem of the intractable KL divergence. So instead of considering probing as just probing or as a diagnostic classification task, they considered a channel that transmits the data from the representation to the target. Yeah, so there's another typo. It should be transmitting from R to T. So the representation is input X and the target is the output Y. So to approximate the mutual information between the target and the representation, they measure the minimum description length of the two tasks, one control task XC to Y minus that of the probing task X to Y. So the minimum description length is equal to the description length of the code length of the model and the code length of data. So the idea is that to describe this channel, you should first transmit a model, and then using this model, both Alice and Bob should encode the sender should encode the data using this model and then send to Bob, and then Bob decodes the data from this model. So the encoded data takes in the L data code length. So in total, you will need the model plus L model plus L data code length to transmit everything. And they propose the MDL to be a measurement of the mutual information between the Alice and Bob, the sender and the receiver. So empirically, the two components are computed as following. So the code length of data is just a cross entropy loss, and although they are encoded in the base 2 instead of base instead of the natural logarithm. So this is in terms of bits instead of nets. If we are taking the natural logarithm, is net. But if you are taking the base 2, it's bits. And the results between bits and net is just it just differs by a factor of constant. And the code length of model, on the other hand, is just the KL of the between the posterior and the prior parameters of the model. So why can the code length of the model be described with this KL? There are more discussions at the bit-spec argument in Hinton and von Kramp 1993 paper. So we were going to skip the bit-spec argument, and we'll just consider that we can use this KL to approximate the code whole length of the model. Note that the KL is not possible to approximate using the conventional neural network. So a straightforward solution is just to change the probing model into a Bayesian neural network so that we can estimate the KL divergence from the prior to the posterior. One of the methods is to first, instead of considering every parameter in the neural network as a parameter, we consider that as a distribution, and that distribution is the collection of the distributions who form a large distribution, and then we can either sample from this distribution and compute the distances between the distributions and distributions, so that we can estimate the KL. And the Walter-Titov paper also offers another solution. This is to approximate the MDL using a frequential coding. The idea is like this: you specify some time steps, T1, T2, T3, all the way to like T10 or T20, depends on how many time steps you want to take. And T1 is 0.1% of the data set, and T2 is 0.2%. And then the last time step is 100% of the data set. And for the first time step, you transmit the first portion using the uniform code. The uniform code is basically without any compression. So the entropy is the largest possible, which is log 2k. And k is the number of labels. And after transmitting the first portion, you can then use the first portion of the code to train a model, and use that model to both encode the next portion of the data as in Alice's side, and then Bob can also use this model to decode the data that Alice compressed using this model. And later, after transmitting the 0.2% of the data set, both Alice and Bob can refine the model using the transmitted data. So after all the transmission are done, the code length is basically the area below the learning curve. So it's approximately the area below the learning curve because it's the cross entropy at T1 and the cross entropy at T2 and then T3, all the way down to the cross entropy of 100% of the data set. So it's similar to the area below the learning curve. And it's a convenient way to approximate the MDL. And empirically, they found that the minimum description length probing is stable across the choices of probe model hyperparameters. So essentially, this solves the problem of which probe to use. We don't need to worry about whether to use smaller models with high selectivity or the more complicated models, which minimizes the KL. We just measure the MDL, take the differences between the control task and probing task, and then this is stable across the choices of probe model hyperparameters. We don't need to worry about which probe models to use. If you want speed, you can just use a small linear model. If you want to be more fancy, you can use a like 3-layer or 4-layer probes with a lot of hyperparameters, also a lot of inner dimensional parameters. As long as you measure the MDL, you're basically good. So there are some additional analysis about the theoretical explanations of why MDL is stable. So it was, I think that this was because MDL considers both the cross entropy terms, the L data, as well as the KL terms L model. So L model is exactly the part that we were not able to approximate and we discarded. So when we consider both the cross entropy terms and the KL terms, the remaining, we essentially shift the 2 KL terms and onto the left-hand side, and computing the left-hand side, including the 2 KL terms, is a much better approximation to the mutual information. So as a summary up to now, in information theory, there is an okay explanation of what to probe and how to probe. So we shouldn't equate high probing performance with rich knowledge in the representation. Instead, we should use the improvement of performance compared to the control task. And the performance, if we're using accuracy or negative log likelihood, there are still some debates, but if we were use the minimum description length, we don't need to worry about this debate. So up to now, we have always considered the probes as classifiers, but recently, the meaning of probe itself has been expanded. We can use some non-classifier models or non-classifier algorithms to be the probes. So if we consider probe as a specified algorithm to test the models, we're still probing the models. But this does not mean that we have to use classifiers. This paper is an interesting example of doing probing without parameters. Instead of attaching a classifier, they use the perturbed masking technique. So what perturbed masking means is that they compute a heat map of the interactions between the tokens and tokens. So for each token, they mask this token and see its impact on the other tokens. So this see how much the representations of the other tokens is perturbed as measured by the Euclidean distance, given by the perturbation or masking of this certain token. And they pass this impact map to downstream algorithms. And they found that this impact map is pretty useful on a wide variety of downstream tasks, including like parsing, classification, or the other tagging downstream tasks. So let's look at some applications of probing. This is, so previously we have seen that the probing can detect whether some certain feature is encoded in these representations. Now, can we remove this feature and see whether removing this feature has an impact to the task? And if we compare the task performance of the model with this feature and without this feature, then we can essentially get a causal impact. And they are using the iterative null space projection, which we will talk about that in the next in 2 slides. And they compare the task performance changes. This helps answer that is this feature used by this task. So this is the iterative null space projection effects. So this is a t-SNE projection of the global vectors of the most gender biased words after 0, 3, 18, and 35 iterations. So the words are colored according to being male biased or female biased. So initially, the words have a lot of information about whether they are male biased or female biased. But after several iterations of this iterative null space projection, they are pretty evenly distributed. So they just essentially removes this male or female gender information feature. The algorithm is summarized here. So in each iteration, they train a classifier from X to Z. X is the vector, and Z is the protected attributes like gender. So the classifier W induces a null space B. So a null space is orthogonal to the basis of this classifier W. So we can see that W is projecting from the current features X to Z, and its orthogonal basis B contains the null space here. And subsequently, they add the null space into the P and use this P to project the features into this null space. So essentially, in each iteration, they try to remove the important features that X includes that could be used to classify Z. And they update the features X using this projected X. So after several iterations, we can imagine that the useful information of X for Z is removed. So eventually the X should be much cleaner than the original one in terms of predicting Z. So essentially, after removing this certain information, they can measure the causal impact of this feature to the corresponding task, and they call this amnestic probing. So this paper in iClear is another interesting application of probing. The probing explains reliance on spurious features. So assume there are only 2 features given the input X. So the T feature is a true feature. So the label is Y if only if T equals 1. And S is a spurious feature. It's basically the other features. The label is 1 regardless of whether S is 0 or 1. So they consider 2 characteristics of the feature, the extractability and the evidence. The extractability is just the frequential MDL of this feature. A larger MDL means it's harder to extract from the human representations in a data set. And they also compute the evidence, which is the proportion of the S-only examples, S equal to 0 and T equals to 1 in the training data. So if we need larger evidence, then the spurious feature is basically disguised better. They found interesting correlations between extractability and the evidence. So To describe these correlations, they compute the relative extractability and the S star rate. They found that if there are significant negative correlations between the relative extractability and the S star rate, basically it means that if the feature is easier to extract, then we do not need too much evidence to figure this feature out. But on the other hand, if this feature is hard to extract, then we need a lot of evidence. Like the model needs a lot of evidence that this data, that the label is true when the S feature equals 0, which is a lot of evidence to let the models realize that this S feature is a spurious feature. So this is an interesting application of the probing, because it draws a correlation between the extractability, which is the easiness to probe, and the spurious features. We will talk more about the spurious features in 2 weeks' time. And the application of probing is still pretty elementary up to now. I believe there will be much more applications of probing in the future. And so as a review, we sort of look at how the probing methods were developed, and we review an information theory framework that explained why this probing should be done as they are done currently. And then we also review some extensions of probing to, for example, without parameters. Yeah, let's